Hi everyone, this is a quick proof showing that if we have two random variables that are independent, then for Borel measurable functions f of x and f of y, the functions of f of x and f of y will also be independent. Just a little review before we get into the proof. We have that this particular setup right here is called a probability space, where omega represents a set of all possible outcomes. Script f is the sigma field of subsets of omega, and p is the set function defined on script f. A sigma field is generated by x, defined on this probability space, if the inverse of, it is the inverse of the Borel set of the real numbers, or the Borel sigma field of the real numbers. So take some time with this setup of what a sigma field generated by x means. It's not particularly intuitive, and it's kind of a really big idea that we're going to be using. We say that x is independent of y if their sigma fields are independent. If their sigma fields are independent, then for their specific Borel sets, or for Borel sets in their sigma field, we have this particular property. And this would be for all Borel sets. So recall I've also introduced capital F of x, which is different than script f, and this is the CDF. Thus, what we want to show to make this proof is the probability. The product of these probabilities implies the product of these probabilities. But what we're going to start with is we want x less than x less than f2, y less than y. We want to show that this particular function is going to be equal to the right-hand side. Notice that we can take the inverse of f1 and f2 to both sides of their inequalities. So this becomes x less than or equal to f1 inverse of x, y less than or equal to f2 inverse of y. Then we have that this is essentially the same thing as saying x is in f1 inverse negative infinity to x, close interval. Y is in f2 inverse negative infinity to y. This is, now that we have it in terms of x and y instead of the function of f and the function of y, we can break this up. X is in f1 inverse negative infinity to x, close bracket. Probability y is in f2 inverse negative infinity to y, close bracket, which is equal to the probability that x is less than or equal to f1 inverse of x, and the probability that y is less than or equal to f2 inverse of y, which is equal to, if we just take the function f1 and f2 on both sides of the inequality again, it's kind of like working this process backwards. Probability f1 of x less than little x times the probability of f2 of y less than or equal to little y. And that's the end of the proof.